Okay. Okay, we are ready to start. Just a short reminder regarding the laboratory exercises. There was supposed initially to be held today, but since we haven't covered all the topics in the lectures that we were supposed to, we changed the actual date for the first laboratory exercises to, I guess, this Thursday. Yeah, am I correct? There is an announcement already on the website. So in the afternoon, you will also have the obligatory preparation for this laboratory exercise. So you have to solve this problem that is given on the website. And you have to send the scanned version of your written report to Branimir Dropulic with his email. You will find the contact information on the web. And the actual laboratory exercises will be done online with Teams. So you will be connected with Teams. Branimir will be giving a short introduction to the topic, and after that you will start to do the actual exercise on your own under his guidelines. And at the end, you will submit some kind of report that you have done appropriately. Okay, then going further back to the last topic that we have covered. So on the last lectures, what we have done is that we have derived the final expression that relates the rate, the output rate, entropy of the output indices of quantizer with the distortion. And this final equation was a very simple linear equation that says that the quality in decibels and the rate or the entropy of the output indices of the quantizers are linearly determined with this slope of 6.02 decibels per bit. So for each bit of entropy, I gain 6 decibels of quality. And this derivation was done for the very simple example, I would say, And that was under assumption that the process is of uniform distribution. So we have assumed that the process has uniform distribution in the range defined by the dynamics of the AD converter from the maximum negative value to the maximum positive value. And in this case, the variance of the signal is simply step size multiplied by the number of steps squared divided by 12. And at the same time, the distortion is step size or quantization step size squared divided by 12. And this ratio is then determined simply by squared value of n, squared value of number of quantization levels. That is the term that you have. So you have the variance of the signal divided with the variance of the quantization error, and this ratio is then simply n squared. And if when taking this square, this power of 2 out of this logarithm, I get 20 log 10 of n. And if I convert this logarithm base 10 to logarithm base 2, then I can get this final relationship between quality and rate. Now, this discussion says, okay, we have shown that we have this linear dependence, that distortion is decreased by 6 dB for each additional bit of rate due to uniform distribution of the process that we have assumed. Entropy coder cannot achieve any additional rate reduction based on variable word length, because all symbols are equally probable. So the only thing is that in the case that the word length is not an integer number, like 3 bits, 5 bits, whatever, because if we have 5 levels, then this word length is 2 point something. It is a fractional number. The only way that the entropy coder can achieve any reduction is maybe by using arithmetic entropy coder and encoding not a single word, but several words in sequence as a real value. And in this case, I can get some gain by taking into account that the actual word length is not an integer number of bits, but some real number, 2 point something bits. But nevertheless, in this case, the actual reduction of the entropy cannot be performed because the process has uniform distribution. It has equal probability of all of the symbols. Regarding the distortion, we have shown that the distortion has to be calculated in each of the intervals, in each of the quantization intervals independently by taking into account the PDF of the process. So in our trivial example, this PDF was supposed to be uniform, and for that reason, this integral was the same for any of the intervals. So this integral has the same form, the same value for all of the intervals I from most negative to the most positive. But nevertheless, if this fx of if this PDF of process is not uniform, then it must be taken into account here, because this is this expectation that we are computing. We are finding the expected value of the distortion in each of the cells, in each of the for each of the levels. Okay, and that is the last statement. So what we have learned that with entropy constrained coding, we can achieve desired output rate of the indices, of the quantization indices, by simply selecting appropriate step size. So that is the one way. So the channel capacity is limited, and I have to constrain the output entropy by selecting appropriate step size. That would give exactly the expected entropy. The other way, if I have to achieve given distortion or given quality, then in this case I can find the required step size to achieve such quality. And based on this step size, I can find out what is the actual rate required to transmit this information. So blah, blah, blah. Now we'll go further to next chapter, and this chapter is high rate quantization, high rate assumption for modeling of ray distortion. So with this first example, we have shown that if we have a process that has any distribution fx of x, then in order to find the distortion, in order to find the entropies, we really have to know this PDF, and we have to integrate based on this PDF to find the distortion for each of the classes. But with this high rate theory approximation, we would simplify this and be able to get the asymptotic solution, asymptotically optimal solution, even in the case where this fx of x, so the PDF is any arbitrary given distribution. So the problem is the following. So what if this PDF is not uniform, as we have shown in this first example, but is some, for example, normal distribution, Gaussian function, or maybe it's a sinusoidal signal, because sinusoidal signal doesn't have uniform distribution. Then what if the process doesn't have a limited codomain? And that means what if the values observed in the signal can be from minus infinity to plus infinity? Okay, in the case of uniform distribution, always the values of the signal were constrained to some range, minus 10 to plus 10, for example. But if we have a signal that has infinite range of values, then how to tackle such a process, how to quantize such a process? So then the next question is, so far we have considered only quantizers that have uniform distribution of quantization levels. So all these quantization steps were of the same size. And maybe this is not the optimal solution for any other PDF except for the uniform PDF. So if PDF, for example, is normal distribution or Gaussian distribution, is this uniform quantizer the optimal solution? Or maybe there is another possible distribution of quantization level, non-uniform quantization levels, that would give lower distortion for such PDF. Then finally, how these centroids, these are these quantization levels, how they should be arranged, how they should be determined in a way to minimize distortion for given entropy, or the other way around, how to minimize the entropy for given distortion. So answers to all of these questions can be found using the asymptotic solution, and this asymptotic solution is based on so-called high-rate quantization theory. The only actual simplification or assumption that is applied here is assumption that this PDF within one quantization level or quantization class can be approximated with constant value. And if I plot this, so for example, I have some PDF, and I have these quantization classes. So one class, next class, blah, blah, blah. And the corresponding centroids values are this one. So these green dots are the central or the centroid values for each of the classes. And what we have density that is a function of x. So this density, fx of x, is some continuous function of x. So x is a real valued number. And the assumption, the only assumption is that we can approximate the PDF of such process with piecewise constant approximation. So I take the central value, I take the value of the density at the central point, at the point of the centroid, and I substitute the actual PDF with this approximative value. So that is the assumption that we are using to simplify the derivation of the optimal solution. Obviously, if this number of quantization levels is very high, so this n goes to infinity, so this is number of levels, this n, if it is a large number, then this assumption is fulfilled, because all of these classes are very narrow, and the actual change of the function of the density is very small within one class. In this example, this change was relatively large. But if I get narrower and narrower intervals by increasing the number of quantization levels, obviously, in this case, this change of the PDF within one interval would be smaller. And that is this high rate approximation. So we assume that this number of quantization level is large. Actually, the output entropy is large in this case because we have many output symbols, and the output entropy is some large value, 3 bits, 5 bits, 10 bits, whatever. And with such assumption, we can approximate that this PDF can be substituted with a central PDF at the position of the centroid. Okay? So this xqi is ith centroid. So the central value of the interval corresponding to index I. So this is this xqi value, xqi. And I simply take what is the density at this centroid value. And I say, in this case, the whole range. So for all x's corresponding to this class, so the class is Ci. So from the lower boundary to the upper boundary, I will approximate that this density is constant. Okay, and why is this a simplification? Because in this case, all the integrals, where normally we have expectation within one class. And this expectation within one class is the integral of fx of x multiplied by some function dx. Now, in this case, this fx of x can be taken out of the integral because it is a constant value. It does not depend on the free variable x. It is a constant depending only on the selected index I of the class. Okay, with the assumption on high rate, with high rate assumption, we find the following solution. And it says here, indeed, quantizer that has uniform step size is the best solution for any input process. So this is very, I would say, strong statement. So not for some processes, but for all processes. The only and the best solution is to use a quantizer that has uniform step size. And somehow this is contrary to our intuition. Why? Because, for example, suppose that PDF of a process is something like this. Obviously, this range of value is commonly observed in the signal. This range of values is also observed, but with less probability, with lower probability. And if I want to achieve small distortion, and if I have a given number of quantization levels, for example, I have only 8 quantization levels. Now the question is, where should I put these quantization levels to achieve the least possible distortion? So logical assumption would be, I have to put it somewhere around here. Maybe. These are the 8 points, 8 possible quantization levels that would model this PDF. So if the density is higher, I would require a smaller step size. If the density is lower, I will allow greater step size. This idea was introduced by two scientists. One was Max and the other one was Lloyd. And for that reason, this kind of quantization is called by the authors Max-Lloyd quantizations. And they decided, they proposed, if I have a fixed number of quantization levels, in this example it is whatever, 9, I should arrange these quantization levels more densely where I have higher density of the probability density function, and more sparsely in the region where this PDF is much lower. It has lower probability. And they have proposed an iterative algorithm how to arrange these values. So how to arrange this, how to find these optimal 8 positions of the quantization level. But this kind of quantization is based on the following assumption. The resolution is constrained. So it is called resolution constraint quantization, or quantization based on resolution constraint. For example, they say, okay, I have only 3 output bits, and I have to decide which of these levels, xqi, from I0 to I equal to 7, if I don't have any entropy coder here. So this is the actual output. The actual output are these 3 output bits without any entropy coding. And they only want to minimize the distortion, nothing else. So they want to minimize, the only criterion that is minimized, they want to find the optimal positions of these quantization levels, xq0 to xq7, in order to minimize distortion given the PDF. So they know this fx of x. They know this function. They know the density of the process. And they want to find the optimal positions on the centroids, but without any entropy coding. So it is only resolution constraint quantization. And with such a constraint, they have found out that there is an iterative algorithm that finds these optimal 8 positions. And this algorithm was later on extended to the case of vector quantization, where we don't have only scalar value that has to be quantized, but we have, for example, a vector with 2 components, a vector with 20 components. And then we again have to find the representatives for each of the classes. In the case of 2 dimensions, it would be, so I have some PDF over 2 variables. Maybe this is something like this. So this one variable x1, x2, and these are ISO probability lines. So these round curves represent points that have equal probability or density of the probability along these curves. So they are ISO probability curves. Where should I put the representatives of such process? Obviously, I would, if I have only 1 bit, I would put 1 value here and 1 value here. And I have 1 output bit that says, okay, it is this representative, so that would be xq1, and this would be xq2, like a vector, xq2. So I have a optimal value for x and y for this representative, and optimal value for x and y for this representative. Okay. What if I have more than, so that would be, doesn't matter, x and then y, to simplify. So I have 2 coordinates, x and y, and I have 2 representatives. Okay. And the concept of finding optimal representatives of a set of vectors. So the process is actually something like this. So these points are the actual process. So we have one process here and another process here. Okay. And now if I add one additional representative, one additional level to model this process, where should I put it? Huh? Maybe I should put it to split this one into two halves. Maybe this and that. And after that, I would have this part corresponds to one of the representatives, and this part of the process is then modeled by another representative. So I have split this process in two parts, and I have better representation. Why? Because the error is then smaller. What is the error? The error is total distance of all points to the nearest point. Okay, I simply add up what is the distance of all process points to the representative. And the optimal solution that gives the least distortion, the least total distance, is the best possible representative with three vectors. So we have three vectors, and these three vectors are the representatives of the process. So the first vector, the second vector, and the third vector. So this here, what I'm explaining, is the so-called vector quantization. It is called vector quantization. And this vector quantization is the context for signal coding, and the algorithm how to design this quantizer. They were designed by three guys, and it is called LBG, Linde, Buzo, Gray. Linde, Buzo, and Gray. So these are the three authors that introduced this algorithm to design an optimal vector quantizer for a given process. In the theory of machine learning, in the machine learning context or in the computer science context, this algorithm is better known as K-means algorithm. So K-means algorithm is actually the same thing. So this is like three mean values. So K is the number of components. Okay, I have three mean values, and I'm trying to separate or to arrange the input process by assigning each sample of the process to the nearest neighbor, to the nearest representative, to one of these three vectors. And the algorithms how to find these three vectors to have the minimum distortion is this K-means algorithm that was then known also as Linde-Buzo-Gray algorithm in the context of signal quantization. Okay? But in this case, what is constraint? Constraint is resolution. So I have fixed number of classes. In the case of EQ, these three representatives, what they do the tessellation of the space. So I have first representative, the second one, and the third one. So how do I do this tessellation of this two-dimensional space? What I do, I simply take the distance matrix. And the distance matrix says if I have this line that connects two representatives, I take the orthogonal line to it, and this symmetral, or this it is called in English something, who would know, divides this space into two parts. So this part of the space is closer to this representative, and this part of the space is closer to this representative. So all points in this half plane are mapped to this one, or all points to this one. But at the same time, bisector. It is called bisector in English. So again, I have this line connecting these two representatives, and this bisector is then this line here, orthogonal to this. And now I have cell. I can finally put also this one, and I have this vertical line from here. So now I have the separation based on intersection of these lines. So everything here corresponds to this value. Everything here corresponds to this value. Okay, and finally, this region here corresponds to this representative. So I have divided this R2 plane, real numbers in 2 dimensions, into 3 regions based on the minimum distance to the nearest representative. Okay? And this kind of tessellation is called Voronoi tessellation. And Voronoi. So the criterion whether one point falls in any of these intervals is simply, okay, if the distance is closest to this one, then it's definitely a member of this red zone, red interval. So what is constrained here? Number of these cells. So number of cells is constrained. Cells. Exactly as was here. So a number of one-dimensional cells. So the first cell was from this midpoint up to minus infinity to this midpoint between these 2 representatives. So this is the first cell, C0, whatever. Then from this midpoint to the next point is C1. Then again, from this midpoint to the next midpoint, C2. So what is again bounded here? We have the bound on the number of these cells. And if the number of these cells is bounded, then this problem is called constraint resolution quantization. But if we have the entropy coder, then the best solution is to use the uniform quantization. And after uniform quantization, what I do, I reduce the rate based on the probability of each of the symbols. So I simply take uniform step size and I extend this value to plus minus infinity. Okay, so that is the idea of entropy constraint scalar quantization. So I don't have the constrained number of cells. I have hypothetically infinite number of cells. Okay? And the only thing that is constrained is the output entropy. So that is the only constraint. So I simply take the uniform step size and I divide the process in equidistant cells. So each of these cells is delta wide. So each of the cells is the same width, delta. How many such cells do I have? Hypothetical, I have infinite number of cells. So n is some large number going to infinity. Okay? Because it goes to minus infinity to plus infinity. So the domain of the signal is, or the codomain, the value of the signal is unlimited. All real numbers are possible output values for the signal. And what I get after quantization, I get index I. And this index I is element of z. Integer numbers. Okay, so this z also goes from minus infinity to plus infinity, but I have integer numbers. Okay. And I construct then the entropy coder for the process with such infinite alphabet. So this process I, so from minus infinity to plus infinity, so this is the dictionary. It has certain entropy because I apply the entropy coder to the output indices. Okay? And if I have this entropy, then I can prove that the optimal step size is exactly uniform step size. So any variation of the step size as proposed by Max Lloyd, or as proposed in the multidimensional case by this K-means algorithm, they are not necessary. The best way to do it is simply uniform quantization. In the two-dimensional case, it's a kind of regular lattice, a rectangular lattice or hexagonal lattice or whatever. You have some regular lattice. And then what you do, you have these indices corresponding to cell positions or to cell identification. And these indices are then entropy coded, and you get the output entropy. So the question is, what is the relationship between the output entropy and the distortion? Okay, or SQNR. SQNR. I want to optimize this relationship. I want to find the best possible solution. So to the highest possible quality for given entropy, or the least possible entropy for given required quality. And the answer is, as we said here, and this answer is can be proved to be true or to be valid under this high rate assumption. And it is true for all processes. So not for some, but for all input processes, irrespectively of the density fx of x. And the final relationship between the entropy and the distortion is this expression here. So this h of I, the entropy of output indices, is related to the distortion. So that is the expected value of the quantization error. So this d is the expected value of the quantization error by this simple expression. So this small h of x minus 1/2 of the logarithm base 2, 12 times d. 12 times d, where this d is, as we know from before, the distortion with uniform scalar quantizer that has step size of delta. It is simply delta squared over 12. So that is the distortion of the uniform quantizer. Uniform quantizer with step size, step d delta. Okay? I can plug this into this expression, and I get the relationship between the entropy, h of I, this small h of x. We will explain it immediately what this small h of x is. And then this 12 and 12 are cancelled. I get simply this 2 and this 2 in the denominator are also cancelled. So I simply get minus logarithm base 2 of delta, log 2 of delta. Okay, so that is the relationship between the rate. So this is the rate, and this is the quality, because this quality depends on this step size. Okay, so what is this small h of x? Who knows? It says here, differential entropy. It is known as differential entropy. Differential entropy. So h of x, this x is a process. And then this differential entropy is defined similarly to normal entropy, but the main difference is that this process is a real valued process. So this x, values of x are element of real numbers. And with conventional entropy, we have defined only discrete probabilities. So we have symbols, how many, if I have coin and if I have head or tails, it is only two symbols, head or tails. And then the entropy is 1 bit, because it is either head or tail. But now we have a real valued process. So this random process is real valued. And this dictionary of symbols is infinitely large. That is the main difference. If I have discrete process, all symbols from the alphabet, so all the letters from the alphabet, it is always a discrete process. I have a given number of symbols. But now if I have an infinite number of symbols, then I have to define the entropy in a slightly different way, and that is instead of sum, I have the integral. So before it was negative sum of pi logarithm base 2 of pi. So that is the definition of the entropy for the discrete case. Now I have, instead of sum, I have the integral. Instead of pi, I have fx of x. I have the PDF of the process multiplied by the logarithm of PDF. Logarithm base 2. Logarithm base 2 of the PDF and integrated over all values of the process, over x. Okay? So you recognize the same elements as before. So this is the probability, this is log 2 of probability, but now instead of having probability, because it was 50-50, for example, for heads or tails on the coin, now instead of having discrete probability, P1 and P2, we have probability density. So this fx of x is the probability density. So I have the expression minus fx of x, logarithm base 2 of fx of x, dx integrated over all values of x. So this is the differential entropy. And by definition, when I have integral fx of x something, then it is nothing else but the expectation of this something. And something is what? It is logarithm base 2 of fx of x. Okay, so if I say what is the logarithm of the density function, it is simply integral of density multiplied by this logarithm of density function dx. So here, this differential entropy is defined as an expectation of logarithm base 2 of density. Okay, and what does it? Sorry, minus. I have to also add minus this one. Okay, minus. What this differential entropy tell us about the process? It is the measure of the complexity of the process in regard to efficiency of the quantization and entropy coding. So this age of x defines how complicated the process is regarding the possibility of entropy quantization, entropy constraint quantization. More complicated process would have higher differential entropy. The process that is more suitable to achieve higher quality for the same rate would have lower differential entropy. Okay, so this differential entropy is a measure how complicated, how complex is the process for quantization. If I have a given number of bits or entropy to quantize this process. For the same entropy, the process that has higher differential entropy would have higher error or larger error, so lower SQNR. So that is the basic interpretation of this value. Okay, and now that we have introduced this differential entropy, this age of x, now we can express the relationship between the rate and the quality. And this is this equation. So this equation is very much similar to everything shown so far. So you know that in the case of uniform process, we had this SQNR was 20 log 10 of 2. This is this 6.02 decibels multiplied by entropy plus 0 in decibels. So if I go back to this expression, so we have derived this expression for the case of uniform process, the process with uniform distribution, that this SQNR for the given number of quantization levels is nothing else but 20 log 10 of 2 hi plus 0 dB. Now I have some term plus SQNR 0 plus SQNR 0. So the first part is the same, but I have this additive term. So this SQNR 0 defines what is the offset of this curve. So this curve is always of the same slope. and the slope is always for 1 bit, I gain 6.02 decibels. This value is this 20 log 10 of 2. Okay? So the slope of the curve is always the same. What is different is this offset value. And this value here would be this SQNR null. SQNR, sorry, I have to realign the whiteboard. For some reason it loses this alignment from time to time. It is quite unpredictable. Okay. So this value, this value, this value. So this is this SQNR 0, SQNR 0. It depends on the type of the process. So whether it is uniform distribution, if it is Gaussian process with normal distribution, if it is sinusoidal signal that has, again, certain distribution of values, okay? And of course, higher value, larger value of SQNR 0 means higher quality for the same rate. So if I compare for the same entropy, H of I, then obviously this intersection would be higher if this SQNR 0 value is larger, okay? So this is this offset of the linear curve. And now I want to express this SQNR 0 based on differential entropy and variance of the process. So this expression here says that if I know the variance and differential entropy of the process, these two values determine what is this offset. So what is this offset of the linear dependence? It is simply 20 log 10 square root of 12 times variance multiplied by 2 to the power of minus differential entropy. So we will show later on that actually this 2 to the power of minus h of x contains inside of itself what? Again, the variance. So finally, the variance would be cancelled. This SQNR 0 would depend only on the type of the process and not on its variance. But nevertheless, the expression is such that we now have the dependence on the variance, on the differential entropy. But once we compute the differential entropy, we will show that this variance is cancelled. So it only depends on the type of the process. Okay? Going further, we have discussed this. Larger SQNR 0 means higher quality for the same entropy. So for processes that have the same variance, sigma x squared, smaller differential entropy implies larger SQNR 0 and therefore higher quality. How we can observe this? We can observe this from the last equation. Okay? So if this sigma x squared is the same for two processes, and if I compare SQNR 0 for these two processes, obviously, so I can remove, this is like a constant for a given variance, which of those two signals would have high quality for the same output entropy. That one which has lower differential entropy. The one that has lower differential entropy would have automatically larger SQNR 0 value, and then obviously better quality for the same output entropy. So for that reason, this H of x is interpreted as a complexity of the input process regarding the quantization efficiency. Okay? Then we have to solve two basic problems once we have these expressions. So we have derived these expressions. Okay? Now we know everything that we have to know. This can be rewritten in terms of step size delta. Which one? This one. Okay? So if I take this logarithm base 2 of delta to one side, what do I have? I rewrite this equation. So this equation was that this h of I was small h of x minus log base 2 of delta of the step size. Or if I take this to the left side, so logarithm base 2 of delta is h of x minus h of I. And then this step size delta is 2 to the power of h of x minus h of I. Okay, so now we have derived what shall be the step size given output entropy of the indices. So this h of I is actually channel capacity. So I have certain channel capacity, this one, and I have a process, x. Fx of x is the density of the process, and this fx of x defines the differential entropy. So depending on the process, I know the differential entropy, and I know the available channel capacity. And from these two values, I can find the required step size to achieve exactly this output entropy that I need to pass the signal to the channel. Okay, now it is 5 minutes after 5, so I'll make a break now. If you have any questions regarding this part, is it clear so far? We will have examples later on, and from these examples you will be, maybe it will be easier to understand how we apply these equations in the actual problems. Okay? So 15 minutes break. in this tab laboratory, multimedia system laboratory, first laboratory exercise, first cycle. Now we have documents, instructions for the first cycle, and preparation for the first cycle of the exercise. Okay. So it is document on 20-something pages that goes to the content of these two exercises, and the one that we are doing the first on Thursday is the second one. So it is DCT-based transform coding of the speech signal. Okay, it says here your task will be to use MATLAB to implement speech signal coding system in the transform domain for compression purposes. You will use discrete constant transform to improve the compression efficiency or to reduce the rate based on the correlation properties of the signal. So far we have not discussed the signals which are correlated. All of these sources were uncorrelated sources. So the output symbols are independent one of the other. But if the sequence of symbols, if the signal is correlated, then it is useful to decorrelate it prior to quantization. Because this correlation is redundancy. It can be modeled in various ways. One way is to do the coding in the transformation domain, and the other way is to do coding on the prediction residual. And this predictive coding we will be covering in the next topic of the lectures. While this transform coding is covered in this laboratory exercise number 1, where we do the transformation of this color signal. We take, for example, 8 samples, and I compute 8 transform domain samples. I compute these 8 coefficients of discrete constant transform. And then what I do, I design 8 independent quantizers for each of those 8 coefficients. Why? Because the first coefficient has the largest variance. It is the lowest frequency one. It has corresponds to the lowest band of the signal. This DCT transform can be also envisioned as a filter bank that has 8 output channels. And in this case, the lowest channel transfers the information about the lowest frequency content of the signal. The second channel of the second higher channel, and so on. And in this way, somehow I'm dividing the signal spectrum into 8 I'm dividing the input spectrum of the signal into 8 equidistant bands. Okay. So this is from 0 to 1/2 of the sampling frequency, or to the Nyquist frequency. In the discrete time domain, we denote this frequency as pi. And what I have the signal then separated into 8 equally spaced bands. And each of those bands is then quantized independently, which is with its own quantizer. And that is the topic of this laboratory exercise. So you will be designing the transfer domain quantization, where you first do the transformation. So I have the time waveform. Okay. I have the time waveform. Blah, blah, blah. Then I take 8 samples, another 8 samples, another 8 samples, blah, blah, blah. And for each of those 8 samples, I compute the transformation, the transform, by simply converting this into a vector and multiplying this with the transformation matrix, M. This is a unitary orthonormal matrix. Okay, and what I get the transform domain coefficients, and these coefficients can be then stacked together. So first block of 8 coefficients from 1 to 8. Blah blah. Next block 1 to 8. Next block 1 to 8. Now I can treat this as a 8 signals. So this is one signal whose rate is 8 times lower than the original rate. Because why? Because I take 8 time domain samples and I convert them to 8 frequency domain samples. And I have the lowest coefficient, how many times? 1 in 8 input samples. So this rate is input rate divided by 8. Divided by 8. Fs over 8. So the rate of the subchannel is simply 1/8 of the input rate. And what I have here the quantizer that was designed to quantize this information, and I have the entropy coder that is designed to reduce the rate of this subchannel. And I have independent quantizer, independent entropy coder for each of the channels. Quantizer, entropy coder. And the information you sent the indices, the output indices of all 8 quantizers that are entropy coded. Okay? And that is the idea how it works. But why it works, do you know the answer why it works? So the effect of this transformation is such that the energy is concentrated into the only small number of coefficients. So here this energy is equally distributed through all 8 time samples. So if I would compute the variance of each 8 time sample, this variance here is the same as the variance for the next sample. For this sample here. So the variance, if I take each 8th sample from the original time domain, I have the same variance for all of these 8 shifts. Shift 0, 1, up to 7. But here, this variance would be the largest, and this variance would be the least. Okay? So you have different distribution of variances. And if you measure the quantity of information based on the variance, then you would say this channel conveys most of the information. So it is most informative part of the spectrum. And this channel conveys the least quantity of information. So only high frequency region that contains maybe only a few bits, much less than this channel here. So if I reorganize this variance in such a way, the efficiency of such transform coding. So what I perform actually here is decorrelation. So this step here, this signal is correlated, so the samples are correlated one to each other. And here, these samples are decorrelated. And after this decorrelation, the variances are spread in an ordered way. So from the largest variance up to the least variance. And if you have such distribution of variance, you can achieve transform coding gain. If the variance here is the same for each of the 8 channels, you don't have any gain. So it is the same as if you would quantize directly in the time domain. But if the variances are of different values, so you have large variance, smaller, 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 then you have the coding gain. And this coding gain, at the end of this introductory note, you will see that this coding gain is defined by the ratio of the arithmetic mean to geometric mean of variances. So this coding gain is a ratio of this mean is simple arithmetic mean. And this here is square root, but power of 1 over n. So it is nth root of the product of variances. So it is geometric mean. You have the ratio of arithmetic mean and geometric mean. This ratio is always greater than 1. because the arithmetic mean is always greater than geometric mean. The extreme case is the process, is the signal that has all equal variances. In this case, arithmetic mean and geometric mean are the same, if all the variances are equal. So the ratio would be 1, and logarithm base 10 of 1 is 0. You don't have any gain. So if the variances of decorrelated channels are equal, then you don't have transformation gain. That will be the case when you have white noise at the input. If you have white noise, then, then the energy in each of these 8 channels is the same. So if the spectrum is flat, so that is a flat spectrum, white noise spectrum, then actually the variance is equal to this average level in each of the bands, and this level is the same. And the variances are the same after spreading or after converting the input signal to 8 sub-signals. All of these 8 variances are the same, and you don't have any gain. But you have gain if these variances are different. So for example, if the first variance is the largest, the second one is smaller, the second blah, blah, blah. Okay? So if you have some kind of decaying variances, then arithmetic mean of variances would always be much larger than the geometric mean of variances. And this ratio defines the transformation domain coding gain in decibels. Okay? That is the main I would like to stress here. Please do the preparation by yourself, and you will also get the ideas how you would actually implement this transform coder. There are step-by-step instructions, which instructions from MATLAB you would use to achieve this DCT-based transform coder. Okay? The last chapter is for those who want to know more, why it works and how it works. Okay. So this last chapter was exactly this derivation of the transform domain coding gain. Okay, now I go back to the original presentation. Okay, so what we have learned so far? We have the expression that relates what? It relates output entropy, so the entropy of indices, as a function of the differential entropy of the process. And here we have also the step size or the distortion of the quantization, D. Okay, that is the first expression. The next expression is a linear relationship between the quality and the rate. And this linear dependence has this offset term, SQNR0, and this offset term, SQNR0, depends on the signal variance. It depends on the differential entropy of the signal. Finally, now we can solve 2 problems. One is, suppose that we have a channel with a given capacity, and we want to find what is the necessary step size such that the entropy of output indices is smaller than the channel capacity. I have simply to compute this difference, differential entropy minus available channel capacity, take base 2 exponents of 2 to the power of this difference, and we have the required step size. The other problem might be, suppose I want to achieve a given quality. So I have a requirement that the quality of the quantization should be SQNR minimum. For example, 40 dB. Somebody requires that the quality must be achieved with 40 dB signal to quantization noise ratio. First of all, based on the PDF of the process, we must find the differential entropy, h of x. Then, once we have this differential entropy, we insert this h of x into the expression for the SQNR0. SQNR0, that was function of signal variance and function of the differential entropy of the signal. Once we have this S squared R 0, I actually insert this value into this equation. So I know this S squared R 0, and I know the required quality. So, for example, this is 40 dB, and this is some offset here. Now I have to find the rate which satisfies this equation. So if I take the rate h of I out of this expression, I have this, what is the required rate for achieving minimum quality S squared R minimum. Simply S squared R minimum minus S squared R 0, which we have found here, divided by this 6.02 decibels per bit. And we get the bit rate for the output indices. Once we have this output entropy, now we can also compute what is the necessary step size to achieve this output entropy. And this is then, again, differential entropy we have already found, minus this entropy of output indices, minimum required entropy of output indices. And these three values then completely define the quantizer, and this quantizer would really have the desired signal to quantization noise ratio, so the desired quality. And we have found out what is the necessary channel capacity to convey this information to the receiving side with this quality. Okay, and now we will solve two simple examples based on theory introduced so far. And the first example will be already the same one we discussed in the case without this high rate approximation, without this high rate assumption, and that is the process that has uniform distribution. So the first example would be the PDF, uniform PDF. Fx of x is uniform. Okay, it has zero mean, so I have this value x, and this minimum and maximum values are from minus square root of 3 sigma x squared to plus square root of 3 sigma x squared. And this density, the height, okay, the height is 1 over square root of 12 sigma x squared. Why, in this case, the area here is equal to 1. So this is really probability density function. And what else? The expected value of x squared is sigma x squared. The expected value of x is 0 because it is symmetrically distributed around 0. Okay? So actually this is the same example that was treated before in the case, for the case without high rate assumption. Okay? Now we have all the elements we need to compute the differential entropy and to compute the S squared R quality and rate ratio. Okay? First of all, we have to find this differential entropy, age of this uniform process. Differential entropy of fx of x. Yeah, this fx of x is uniform. And since this fx of x is a constant value, so by definition, it is again negative integral over x, fx of x, logarithm fx of x, logarithm raised to fx of x, okay, dx, blah, blah. But all of this is constant. All of this is constant. So I can take this in front of the integral, okay, and what I have within the integral is simply the integral of dx in the range from minus, from this minimum value, from min to max value. Okay? So I get this constant times integral dx from min to max. Okay? So this constant here is this density times logarithm base 2 of density, blah, blah. And this integral of dx from the minimum value to maximum value. And that is simply the difference of the upper bound minus lower bound. After canceling whatever I can cancel, I get the final expression. So this differential entropy for the uniform process is logarithm base 2 of square root of 12 times sigma x squared, so 12 times variance. So the variance of the signal multiplied by 12, I take the square root, I take the logarithm base 2, and I have the differential entropy expressed in the number of bits. Okay. Now that I have this differential entropy, I can find this S squared R 0. So this is the offset of the rate distortion curve. So what is this S squared R 0? So for the uniform process. So for uniform fx of x. Then I use this original expression for this S squared R 0. It is shown here. Okay, 20 log 10 square root. So this is 20 logarithm base 10 of square root of 12 sigma x squared. And then multiply 2 to the power of minus h of x. Okay? And this here, this term here, h of x, was logarithm to square root 12 sigma x squared. Okay? Then obviously these two are cancelled because this 2 to the power of logarithm 2 of the same thing. So actually this here and this here is cancelled, and I get the value of 1. And the logarithm base 10 of 1 is 0. Okay? So I get that this offset of the rate distortion curve for the case of uniform distribution of the process is 0. Okay, sorry, here 0 dB. So S squared R for the uniform process is 0 dB. And of course, this is the same expression we had before when we didn't assume this high rate approximation or assumption. So without this high rate assumption, we had this linear expression with 0 offset. So it was 20 log 10 of 2 times entropy plus 0 dB. So this 0 dB, this is exactly this S squared R 0. So for the uniform process, the offset is 0. Okay. Then going further, now we will try. Okay. Now we also want to find what we want to find the step size. Obviously, the relationship between the quality and the entropy, it has 0 offset. It is the same as the result we had previously in the case of process of uniform distribution. Quantization step size delta for the given output entropy can then be found based on the variance of the signal. And it is by simply inserting this differential entropy into the expression for step size. The step size delta was 2 to the power of h of x minus entropy h of I. Okay? And after inserting the actual value of this entropy, and that was log base 2 of square root of 12 times sigma x squared. Okay? I get then, that is nothing else but this square root of 12 sigma x squared multiplied by 2 to the power of minus h of I. Okay, and that is the expression that tells you what should be the step size if you have given channel capacity. So you have, for example, 3 bits per simple channel capacity. In this case, for the process that has uniform distribution, I have to select the step size based on the variance of the process. Okay? And this is simply 2 to the power of minus 3. For example, if this age of I is 3 bits per symbol. Okay, in this case, you would get delta is square root of 12 sigma x squared divided by 8. Divided by 8. Okay? And it also shows one obvious result, that increasing the entropy by 1 bit, so if I have age of I prime, that is age of I prime, that is equal to age of I plus 1. Okay, so if I add one additional bit to the output entropy, so now I have 4 bits per symbol. Now the step size delta prime would be the same value here, 12 sigma x squared divided by 16. So I have the step size that is twice smaller, 2 times smaller. So by increasing the rate by 1 bit, it means that the step size must be decreased by 2 times, in half. Okay. Going further, now once we have derived this trivial example, now we will go to a more complex example, and this example is the normal distribution or Gaussian distribution. So the Gaussian white noise, so the signal that follows this Gaussian distribution is the one that has PDF of this form. So the PDF of the signal must be of this form. This term here is this exponential function of minus x squared over 2 variance, 2 times variance. So this is this core of this exponential, of this normal distribution. And this term here is this normalization term that ensures that the integral of this fx is equal to 1, to unity. So if I integrate this fx normal of x over the whole range of values, x from minus infinity to plus infinity, I get integral that is equal to 1, to unity. What only shows that this fx of x is really a density, is probability density function. Okay, that is the condition that any probability density function must fulfill. But its integral must be equal to 1 over the range of random signal values. Okay, but what is the main difference in comparison to the previously shown example with uniform distribution? First of all, this value of x can be any value from minus infinity to plus infinity. In this example, it was from min to max. Okay, so obviously, in the case of uniform distribution, it was minimum value minus square root of 3 times variance, or to the maximum value square root of 3 times variance. But in the case of Gaussian distribution, you have the values that are from minus infinity to plus infinity. Okay, and if I have this PDF, I can also find the cumulative density function, the CDF, and this CDF is defined by the so-called error function. So this RF is known as error function. There is also error function complement, RFC. But what we need so far is only this error function. Error function is some ugly function, I would say, defined using this expression, integral from 0 to z exponent of minus t squared dt, and also normalized with 2 over square root of pi. So this is this error function. It is numerically implemented in MATLAB or any other statistical tool. And based on this error function that defines cumulative density function, we can derive differential entropy. So what we want to derive is this differential entropy h of x for the Gaussian distribution of input random signal. So we want to find this h of x. So not uniform, but now x normal, Gaussian distribution. Now what we have here constant part of the PDF. So this is this normalization term. We have this exponential part of the PDF. Exponent minus x squared over 2 times variance. Now we have the logarithm base 2 of the density. So this is logarithm base 2 of the input density, dx. Okay, so this is the same as before. But now what we can do, we can find this logarithm by converting the logarithm base 2 to the natural logarithm. And that is done if I simply place 1 over natural logarithm of 2, then instead of writing logarithm base 2, I can write logarithm base natural logarithm, ln. Okay? So this ln is this first part, ln of this constant part, I would say, because this sigma x squared is a constant, variance. And this second part is the logarithm of the second part, exponential function of minus x squared over 2 times variance. And since it is natural logarithm, then this natural logarithm of the exponential function is nothing else but the argument of this exponential function, and that is minus x squared over 2 times variance. So I have divided this logarithm base 2 of the second part into first part, it is constant part, and the second part is this x squared times something. Okay. Now what I have to integrate this exponential function multiplied by this constant term, or exponential function multiplied by x squared dx. Okay? And these two terms, this constant term and this x squared term, are shown here. For the first term, I recognize it is simply the integral of the PDF over the whole singular range from minus infinity to plus infinity. I know this is equal to 1 because this fx of x is the PDF. So its integral must be 1. And what is left of the first term is a constant shown on the left. Of the second term, I have this integral of x squared times exponential function of minus x squared over 2 times variance, dx. And this integral can be also found in some tables. So in some tables, so if you use some symbolic toolbox for integration, you would find that this integral exists. In the indefinite form, it is this solution. And then I have to insert the bounds, the lower bound and the upper bound, from minus infinity to plus infinity. And if I insert these bounds into this expression for x, I would get two parts. One part is this part here. It is simply exponential function. And the second part is this error function. So this error function that was discussed at the beginning, that defines the cumulative density function of the PDF, or of the process. So this error function is the second part of this expression, of this integral. And I have to evaluate the error function of the upper bound minus error function of the lower bound. This error function of plus infinity is equal to 1, while error function of minus infinity is equal to minus 1. So the first term is cancelled on the upper and lower bound, and it vanishes. While the second term, it has this 1 minus minus 1, it is 2. Okay, then this 2 and 2 is cancelled, and I get only this as a result. So this integral here is simply square root of 2 pi variance to the cube. So sigma x to the 6th power. Okay? And by inserting all this solution into the final expression for the differential entropy, I get this first term. It was this first part, this constant term here, and plus the second term. I combine all of this first term, second term, third term, all together. And I get, this is the solution. By finally converting back to logarithm base 2 instead of the natural logarithm, I have the final expression that expresses the differential entropy as 1/2 logarithm base 2 of 2 times pi times e, so this is the base of the natural logarithm, and variance sigma x squared. So this is the differential entropy of the normally distributed process. So if I have a Gaussian process, its differential entropy is defined by its variance. Okay, so that is the way, that is the reason that I told you before that this variance would be cancelled once I insert this expression for differential entropy into the expression for S2R0, for the offset. So because here in the expression for the S2R0, I have 10 log 10 of 12 times variance, and then multiply by 2 to the power of minus 2 times differential entropy. And this 2 to the power of minus 2, so this 2 and 1/2 are cancelled. So this logarithm base 2 is just putting this into the denominator, okay? So this 2 to the power of minus log 2 is nothing else but putting this value into the denominator of this ratio. And after cancelling everything that I can cancel, you see here that this sigma x squared is cancelled. And I get that this S2R0 is only determined by the shape of the process, by the type of the process, and that is, in this case, 10 log 10, 6 over pi times e. So the e is this natural logarithm base, okay, 2.7 blah, blah, blah. And I can actually compute what is this value. This value is minus 1.53 dB. Minus 1.53 dB. So actually it shows that this S2R curve for the normal distribution is lower than the S2R curve for the uniform distribution. So if I would compare two curves, so this is S2R for uniform, because it has this zero value, S2R0, is equal to 0 dB. On the other hand, the normal distribution has the same slope as S2R normal, but it has negative offset. So this offset, S2R0 for normal, is minus 1.57 dB. 53, sorry, 1.53 dB. So for the same entropy, it has lower quality. So if I would compare these two processes for the same entropy h of I, or the output indices, I would have lower quality for normally distributed process in comparison to the uniform distribution of the process. Lower quality. And it says further on, now we can also find the required step size. What is the required step size in this case? If I have a given channel capacity again, so I have this h of I that is defined by the channel capacity, and I again insert into this equation 2 times 2 to the power of differential entropy times 2 to the power of minus rate, minus h of I. Okay, and I get this expression here. Finally, we conclude that this normally distributed process has 1.53 dB larger distortion than the process that has uniform distribution for the same input variance and for the same output entropy. And the reason for this is that actually the step size, the required step size for the normal distribution to achieve the same rate must be larger, 1.193 times larger than for the same case with uniform distribution. So this uniform distribution is, let's say, I would say, less complicated to quantize than the normal distribution. If I have normal distribution, the step size must be larger. And automatically it means distortion is larger, quality is lower for the same rate. And this ratio between the step size, normal distribution, uniform distribution, is this 1.193. 1.193. Okay, finally, it can be theoretically proven that the normal distribution process is also the worst possible, the most complex process in regards to efficiency of entropy constraint scalar quantization. Of all the processes, this normal distribution is the worst. Why? Because it has the highest possible differential entropy. So if you would compare all different processes that have the same variance, and you would find out that this process, normally distributed process, has the largest differential entropy of all processes sharing the same variance. So for that reason, the normally distributed process is the most complicated or the toughest signal to quantize. In that sense, if you don't know the PDF of the input process, so it is some arbitrary distributed signal, then you can always use normal distribution as a worst case scenario. So it is the lower bound. So the worst you could achieve is normally distributed quality for the normally distributed process. For any other process, the quality would be higher for the same variance and for the same output rate. Okay, so the differential entropy of any other process with the same variance is always lower than the differential entropy of the normally distributed process. And that is the reason why this Gaussian process can be used as a template that defines the bound for the quantization quality. So the lowest quality for given entropy and given variance. Okay, so in these two examples, we have shown that the scalar quantizer that has bound on output entropy, because it combines the uniform scalar quantization with entropy coordinate, can be designed and theoretically analyzed even for processes that have infinite dictionary. So this function is real valued, this process is real valued, but of infinite values. So from minus infinity to plus infinity, as is the case for the Gaussian process. While actually in the practice, we understand that since we have to design the entropy coder, the actual set of symbols is nevertheless always bounded, because we have to construct a code for each of the output integer values. So we have this AD converter, we have these indices at the output of AD converter, and these indices in the end must be encoded with a variable word length code. And this code must somehow tabulate all possible values of I. So we have all possible integer values, and for each of these values of I, you have the corresponding code that you will send over the channel to transmit this information. And that is the practical limitation why you always have to bound the range of values, bound the range of these indices at the output of the AD converter, due to implementational reasons, not to theoretical reasons. As far as theoretical reasons are concerned, this process can be unbounded regarding the values. But due to the limitations regarding the actual implementation, to construct the code book, you have to bound the values of integer to some range. And then you will say, okay, if this value is below this least possible value, I will always truncate it to this least possible value. Again, if it is larger than the largest positive value, I will always use this code, the largest positive code for this value that's above. And after the break, we will show how this works in MATLAB. And actually what you would use in this laboratory exercise on Thursday, you would use part of this code that is shown here as a reference how to do the entropy constraint scalar quantization in the time domain without any decorrelation, so without any transformation. I simply take values of this scalar signal and I quantize each of these signals based on uniform scalar quantization, and I simply add an entropy coder at the output of this AD converter. So I have these indices, I construct the entropy code, and I have the actual entropy of the average rate of these symbols on the channel. I have the entropy and the average rate. And finally, of course, this average rate would be close to the entropy, slightly above the entropy. Okay, after the break, we will show how it actually works. For examples of 3 signals, it would be sinusoidal signal or noise signal with normal distribution, or finally sawtooth wave, like a linear signal of a given frequency. Okay, so that will be 3 types of signals that we would be discussing or simulating. So what would be the entropy, what would be the quality for the given entropy. Okay, now we'll make a break, so it is 1 minute after 6. 10 minutes break, I guess it is enough, huh? We'll try to finish 5 minutes later. I have to take the paper for the attendance. write the attendance for today's lecture. Okay, I will now show you the main parts of this MATLAB script that we'll be using for the laboratory exercises to explain the critical parts, I would say. So first of all, we define the time domain axis. So this is the range of indices from 0 to capital N minus 1. And then we define we select one random frequency for the signals that are periodic, and that would be for sinusoidal signal. And for the sawtooth wave signal, we have the period or the frequency. In this case, I select this value omega or W from 0 to 2 pi. That would be phase increment between two time samples. The same as we had before for the case when we simulated quantization. So if the signal is of type 1, then we simply compute this sinus of omega times n. So for each new time sample, I increment the phase by W. So this is the actual phase increment depending on the chosen frequency omega. If the signal is a random noise with a Gaussian distribution, I use the built-in function of MATLAB, random normal, random normal, and I simply say, okay, create a vector of dimension of n samples, row vector with n random values according to the normal distribution. Finally, if I have the sawtooth wave signal, then I compute the instantaneous phase, the same phase as for sinusoidal signal, omega times n. And I simply take the principal phase value. So I remove any integer multiple of 2 pi. So as soon as the phase, as soon as this accumulated phase value exceeds the value of 2 pi, I wrap it around and I go back to 0. Okay, so this is nothing else but removing this integer number of full circles, or the full number of integer number of periods. Okay, and I have this fractional part and I use this fractional part after dividing by pi, I get the value from 0 to 2, because this is from 0 to 2 pi. So if I divide 1 over pi, I will get from 0 to 2 values, okay? And then if I simply remove, if I subtract 1, I will get the values from -1 to +1. Okay, I will get the linear change of the amplitude from -1 to +1. Okay, this y. So y is the signal. Then after that, I remove the mean value of the signal, and I normalize the signal such that it always has unit variance. And in MATLAB, it can be done with this expression. So to remove the mean, I say simply y is y minus mean of y. After that, y it has 0 mean after this command. And with the second command, I divide the signal by the square root of the variance. And after this command, the variance of the signal is 1. It is unit variance. So with the first part of the program, I have created either sinusoidal signal or random noise signal with Gaussian distribution, or sawtooth wave signal, all three with unit variance and 0 mean. Now I compute the differential entropy according to theoretical expression we have derived. So for the Gaussian distribution, for example, if you remember, for Gaussian distribution, this differential entropy was square root 2 pi variance, okay? And, sorry, not the final expression is this one. Differential entropy 1/2 logarithm base 2 pi e variance. So it must be logarithm base 2 pi e, 1/2 of that. We can check if this is really true. Differential entropy for normal distribution, 1/2 logarithm base 2 pi exponent of 1, that is e, times sigma square, but sigma square is of course 1. It is just for written for the general case. If sigma would not be unit sigma, unit variance, then I would have this sigma square also in the expression for the differential entropy. But in my case, this sigma is equal to 1 because all of these three signals are normalized to unit variance. And for that reason, I can say, okay, sigma is equal to 1. The same thing is for the sinusoidal signal. It is not in the materials for the lectures, but you can also try to derive the differential entropy for the sinusoidal signal the same way that we did when we discussed, okay, this is a random, that is function of a random variable. And when computing the expectation, the random is instantaneous phase. So I have uniform instantaneous phase, but this function y is a function, deterministic function of a random variable, which is instantaneous phase. And for such a random function, you can also find all of the second moments, okay, so the expectation, the variance, but also the differential entropy. Differential entropy can be also found for sinusoidal signal, and differential entropy for the sinusoidal signal is similar to the differential entropy for the normal distribution, but it has only p squared instead of 2 pi exponent of 1. It has p squared times sigma squared over 2. Finally, for the sawtooth wave signal, I have the expected expression that we have derived. It is the same as uniform distribution. So for the uniform distribution, uniform differential entropy, blah, 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 log 2 of square root of 12 times variance. So differential entropy for the uniform distribution must be of this form, logarithm base 2 square root of 12 times variance. Let me check it if it is written here. So for the uniform distribution, what corresponds to triangular signal, 1/2 logarithm base 2 12 times sigma square. 1/2 is because it is square root. So logarithm base 2 of square root, then it is the reason why we have 1/2 in front of the logarithm 2. So we have now defined the differential entropy for all three types of signals. Now we have H of x, that is differential entropy, and we also have the capital H, which defines the channel capacity. So we have selected certain channel capacity. It is in the code in front. We have in this initialization of this capital H on a given value, for example, 3 bits. And based on this differential entropy, based on the channel capacity, I find out what is the required step size capital D. Once I have this capital D, I can find out what is the expected distortion, because the expected distortion is simply squared step size divided by 12. So the expectation of the squared quantization error is 1/12 of squared step size. Okay, now that we have this expected distortion, we can also find the expected SNR ratio, signal to noise ratio. It is then variance of the signal. It is 1 because we have normalized all 3 signals to unit variance. And in the denominator, we have the expected quantization error. So E error expected. And computing this value of this 10 logarithm base 10 of this ratio gives us what would be the expected SNR for the chosen entropy. Now that we have computed all these expressions are based on theoretical derivation. Now I can actually apply this step size to do the quantization. So I apply this delta. I use this delta, capital D, I round this ratio, signal divided by the step size, to get the index. So yi is the output index of the AD converter. And after multiplying this index, yi, with the step size, I get the quantized output value. And the difference between the input value and quantized value is the quantization error. ER, so is the quantization error with the chosen step size capital D. Now that I have the error for each of the time samples, I can find the mean squared error as approximation of the expected squared quantization error. So this capital E error is an estimate of the expected quantization error. At the same time, capital E of Y is actually the expected value of the signal squared. So it is what is the expected variance based on sample mean of the squared signal value. And then by taking these two values into ratio, I would get what is the actual ratio between the signal variance and quantization variance. After quantizing the signal with a uniform scalar quantizer with the chosen step size capital D. So this capital D is this delta. Okay, so we have the expected SNR, we have the actual SNR. Finally, we have to compute the expected and the actual entropy. Okay, so these are the remaining two quantities we have to find. So first of all, we have to compute the actual entropy of output indices. So we have this yi is this integer output index of the AD converter. I take what is the minimum value of yi and maximum value of yi. And I construct a range of values, yi minimum to yi maximum, and I simply count how many times I have observed each of the values in this range. And for this I use the histogram function. This histogram function, if I give as an input the signal, not signal, but the signal indices, the output indices of the AD converter, and if I give the input a range of values from minimum to maximum values, then it simply counts how many times each of these values is observed in the input signal, in the, not signal, but quantized indices of the signal. And once I have this histogram, I simply divide the histogram with the total number of samples, and I get the discrete probabilities of observing each of the symbol values. So from the minus negative value, okay, from the largest negative value to the largest positive value, what is the probability of observing each of the symbols? Once I have this probability, so this is discrete probability, I simply compute the entropy according to the expression sum of pi times logarithm base 2 pi. So this is pi, and this is logarithm base 2 pi, and this is a sum because it is the multiplication of a row vector and a column vector. So this is transposed. This second part is transposed. So I have this column vector. It is logarithm base 2 of the probability, or the pi, and this here is a pi as a row vector. And if I multiply this row vector with a column vector, it is simply a scalar or inner product, and I get actually a sum. First by first, second by second, third by third, and I get exactly the expression for the entropy. Negative sum of pi times logarithm base 2 pi. So what I have here the entropy. But what I have to do also, I have to exclude those symbols that I have not observed at the output. Because for any reason, some of the symbols in the range from min to max might not occur at the output. So it was not observed. And if I would take the logarithm base 2 of 0, because I have 0 count for this value, I would get minus infinity. And I would not be able to compute this sum. And for that reason, I simply exclude those symbols for which the PDF is 0. So I take, so code postoji, so code exists, only for those symbols for which the PDF is above 0. And so instead of computing the sum over all output symbols I compute only the sum over the symbols that really exist, that are observed at the output. Okay, so far we have computed also the actual entropy of the output of the AD converter. Finally, we will also compute the expected PDF and the entropy of the output indices by what? By differentiating the analytical CDF of the input process at the edges of the quantization levels. So as we said before, to find the probability of, if I have some PDF, then CDF is the integral of this. It must be monotonically rising curve. Okay, so this is CDF, it cannot go down. Okay, it must only go up and up and up. Okay, let me draw it once more. So CDF will be and it goes to 1. Okay? So instead of computing the integral below the PDF curve to find the probability around one quantization level. So this is the midpoint, this is another midpoint, and I have to compute the integral below the PDF. The same thing can be done by simply taking the difference of the CDF. This value and this value. So I differentiate these two values and I get this integral. Okay, so the differentiation of CDF gives you what is the probability of this class. So this class from lower bound to upper bound, these two bounds are midpoint between two quantization levels. Okay? And now I do it here symbolically, not symbolical, but using the analytical expression. Because for all three types of signals, I have computed what is the CDF curve, so the red curve. The red curve is, for the case of sinusoidal signal, arcus cosinus of this minus argument over pi. And the argument is, I just have to ensure that this argument is within the range of plus minus 1. Okay? What is the argument? The argument, so I find these quantization levels and I find these midpoints. So these are these arguments, okay? I find these are the quantization levels and these two are midpoints, okay, midpoints. And these midpoints are these arguments, okay? And once I find these argument values, I will simply differentiate this CDF. It is done here. I use the diff function in MATLAB. It simply takes the difference of two neighboring elements in the row vector. Okay? So once I have the CDF for all these bound values from midpoint to midpoint, okay? Once I have this CDF value for all these midpoints, I simply differentiate this CDF and I get the probability for each of the indices. Okay, I get the probability for each of the indices. And this is the theoretical probability. It is based on the PDF or CDF of the signal and not on the actual realization. Because what we have here, once we construct the signal, where is the signal here? It is only one realization of this stochastic process. It has only n samples. But normally this signal has infinite number of samples, and this infinite number of samples, they are described by the statistical interpretation by the PDF of the signal. And if I have the PDF, this PDF completely defines the signal, completely, analytically. I can compute the probability for each of the quantization classes. What is the probability of observing the symbol? But in the actual sample, so if this sample is only n times samples long, it might occur that some symbols are not observed at the output. So because simply they are skipped, depending on the randomly chosen frequency. And for that reason, this empirical entropy, empirical probability is this PDF based on histogram of the observed symbols. This empirical PDF is different from this expected PDF derived from the theoretically described CDF of the process. Okay, now that I have this PDF, expected PDF based on the density of the process, I can also compute what would be the entropy of such PDF. Now I don't have to bother about non-existing codes, because now the probability for each of the classes is non-zero. And I can compute a normal scalar product of the PDF times log2 of PDF. Okay, and I get the expected entropy of the output signal. Okay, now that I have described all the main parts of the program, I will do the actual simulation in MATLAB. But before doing the simulation, let's us just describe what we would simulate. We would simulate a process that is based on a sinusoidal signal with unit variance. It means that the maximum value is square root of 2. Because if it's unit variance, then the maximum value is square root of 2. And this ideal signal is, ideal signals are blue points. So blue points, they represent the ideal value of sinusoidal signal. The green line are the quantized values if I use the entropy of 3 bits per sample. So I apply the entropy coder, I select the appropriate step size to achieve this output rate of 3 bits per sample, and by applying such quantizer, I would get the quantization values. So this level here, this green value, is different from the actual blue value. This green value is close to this blue value. This green value is also close to this ideal blue value. In this case, this green value is a bit further from the ideal value. And once I have this quantized green signal, I will interpolate, using ideal interpolation, this red curve through the quantized samples. And you can observe here that this red curve passes through these edges of the green step. Green step, green step, green step here, green step here. So they miss the blue dot, but they go through the quantized value through this green step value, okay? And what I have this interpolated signal. Now I can find the difference between the green step and the blue input value, and the average squared difference is this quantization error, the expected quantization error. So this is for the sinusoidal signal. This is for the case of a random signal with Gaussian distribution. What you can observe is that now the range of values is much larger. So although I have unit variance, I observe values that are of large amplitude, for example, 2.5, almost 3. Okay? So with Gaussian distribution, the range of value is much larger than the variance. So the variance was unit variance, 1, exactly as here, unit variance. But here the amplitude was limited to square root of 2, so 1.41. But here this maximum amplitude, theoretically, was infinite. So there is a very small probability of observing enormously large values of the signal with normal distribution. Okay? And finally, the same example with the same output entropy, with the same unit variance, but these blue dots are on ideal sawtooth wave, so ideal linear function. And after quantizing these ideal linear values, I get the quantized values. This one that is close to this one, but in between. This one also misses this ideal value. Again, here I have the error. Here the error is smaller. Here the error is large. This value here, blah, blah, blah. Okay, and I interpolate this red curve through the corners of this green quantized value, and I get the interpolated quantized signal. Okay, finally, now I will show here what is the probability of output symbols for each 3 signals. Okay, so first one is for the sinusoidal signal. I have the entropy, in this case, chosen as 1 bit more. I have 4 bits per symbol, output entropy. If I would use binary code, I would expect how many symbols? 2 to the power of 4, so 16 symbols. I would expect to observe 16 symbols at the output. But if I use the entropy code, I can observe that actually I have 21 symbols. So the step size is such that in between the least negative value, so the largest negative value, minus square root of 2, to the absolute, or to the positive value, square root of 2, I have how many levels? I have 21 different levels, 21 symbols. Okay? Why 21? Because I have the entropy coder after the quantizer. So this entropy quantizer would reduce this rate from logarithm base 2 of 21, which is definitely larger than 4, because 21 is 2 to the power of whatever, 4 times something, I don't know how much. But with the normal binary code, it would be 16 symbols. Now I have 21 symbols. 21 symbols for the same range of values. Okay? But the entropy code would reduce this final rate to only 4 bits per symbol. Why? Because the probability of these values, large positive or large negative, is much higher than the probability of 0 value. So when this cosine function passes through this 0 value, it passes very fast, very, very rapidly. And statistically, if you would count how many times you have observed 0 value, much more seldomly than for the value of plus or minus 1. And since I have different probability for different symbols, I can achieve reduction based on entropy code. And that is the reason why I have 21 symbols, and still I have the output entropy of 4 bits per symbol. With normal distribution, for the same output entropy of 4 bits per symbol, I have 38 symbols. Why? Because now I have really significantly larger differences in probability for some very large symbol values, almost minus 5 or to plus 5, and very high probability of observing 0 value. So the symbol 0 is observed most of the time. Plus minus 1, a little bit less. But for example, this value, plus minus 4 point, I don't know how much, 4.6, is observed very seldomly. And that is the reason why I can have 38 symbols, but still have the output entropy of only 4 bits per sample. Okay? obviously, those symbols would have much longer codes, longer word lengths, while these symbols would have shorter symbol lengths. Okay, and I would construct this kind of entropy code in the Huffman or arithmetic code, encode this symbol, and I would approach this entropy value. Okay, it would not be ideally 4, but slightly above 4. Finally, for the uniform distribution, for this sawtooth wave, we expected to observe the same probability for all of the values, because it is uniform distribution. We have observed half of the probability for the largest and the lowest, for the largest negative, for the largest positive value. Why? Because this first and the last class is twice narrower. Okay, I don't have the full width of the class because I have only half of the quantization step for the first class, most negative class, and for the most positive class, and that is the reason why the probability of those two extreme values are twice lower than the probability of all other values. Okay, so we have what? We have 3 different signals, we have 3 different probabilities, and 3 different total number of symbols, I would say, okay? So 3 different total number of observed symbols. Is this true? So is it really only 38 symbols? In this case, no. Theoretically, it is unlimited, okay? Because Gaussian function has non-zero probability for all values to minus infinity. Very small probability, but non-zero. But nevertheless, in practical situation, I would truncate. I would say, okay, it is 38. I construct the code for these 38 symbols, and I would have this entropy of 4 bits per symbol, and finite code book for these 38 symbols. For all the values that are below this -5 or above this 4.6, I would take this last value, the least negative or the most positive value, as a limit value. Okay? Now, these plots, they show what? They show the model. So this blue line and these green crosses, they show the expected quality for the given entropy. So I have selected 1 bit per symbol, 2 bits per symbol, 3 bits per symbol. So these are the ideal desired rates at the output. 1, 2, 3, blah, 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 up to 16. And the ordinate value is the expected distortion for this rate. And this was computed here with this expression, with this first expression. So the expected error, the expected SNR, is this and this value only given by the rate, by this age. So age defines the rate. So this rate defines the step size. Step size is used to find the expected distortion, and this expected distortion defines the SNR ratio. And this is this linear relationship between the quality and the rate. And it only the slope of this linear dependence is always the same, 6 decibel per bit. So the slope is always the same. But if I change the type of the signal, you can see that this blue curve is going up or down, okay? Depending on the type of the signal, down, up, okay? So only the offset of this linear curve depends on the type of the signal. Whether it is Gaussian normal distribution, if it is sinusoidal signal, or if it is uniform distribution like a sawtooth wave signal. So this blue line and then these green crosses are the expected, ideal behavior. So this is this high rate approximation. I have this theoretical high rate approximation. What is shown with this cyan color and these red dots is what is the actual entropy and the actual distortion. Okay? For the first case, it is a sinusoidal signal. I desired, I wanted to have the output entropy of 1 bit per symbol, but I got 1 point something, 1.5 bits per symbol. And distortion was not this value, but it was signal to noise ratio. So this SQNR was not the expected value, but some larger value, but at much higher rate. So instead of 1 bit per sample, I have 1.6, 1.5 bits per sample, per symbol. Again here, I desired 2 bits per symbol with this distortion, expected distortion. I got almost 3 bits per symbol with the distortion that was slightly below, okay? But again, I'm operating below this expected curve, below this rate distortion curve, high rate approximation. But as this rate increases, then this approximation is more and more accurate. So you can see that these red dots converge to these green crosses. As this rate increases, I really achieve this high rate approximation. Really, this high rate approximation is achieved. And this approximation is practically identical to the empirical observed distortion and empirically observed rate. Okay, so that is the reason why we say that this is high rate approximation. For lower rates, this approximation is not valid, and of course, we have this divergence, but nevertheless, it is not a big difference. So even for very low rates, you could still predict the behavior of the quantizer with this high rate approximation curve, with this blue line, okay? And this deviation from this high rate model is practically largest for the sinusoidal signal. So the first one is sinusoidal signal. It has the largest deviation from this high rate model. For the Gaussian noise, it is practically ideally fitted. So this prediction is almost ideally observed in the actual empirical entropy and empirical distortion. I have only this slight deviation at 1 bits per symbol. As soon as I have at least 2 bits per symbol, these empirical values are practically identically equal to the theoretical values. For the uniform distribution, it is sawtooth wave. I have again a bit deviation from this theoretical expected value, but as soon as I'm operating at least 4 or 5 bits per symbol, they are following each other closely. Okay, so that is the reason why this high rate approximation gives us very good insight into the operation of the quantizer, into the expected operation of the quantizer. And this code, finally, if I go to MATLAB, so this code is this MT02 quant enter entropy. So just a slight walk through the code. So if I activate demo mode 1, then it will show all the figures individually for each of the signals for one chosen frequency. If this demo is equal to 0, then it shows only the last curve. This SNR curve is shown for all different rates that you compute. If you want to get this rate distortion curve, this HV vector defines the desired output rate, desired H of I. And this H of I goes from 1 bits per symbol up to 16 bits per symbol. If you use only this demo mode for one choice of output entropy, then you select this value of number of bits per symbol here as 3 in this example. Now you have defined the sampling frequency, the number of periods shown for the displays, for the plots. Okay, the total number of samples for this realization is 100 samples. But if I use this demo, then I use only half a second short sequences that I can reproduce on the speaker as 1/2 of the second sequences. You select here the signal, 1, 2, or 3, sinus, normally distributed noise with Gaussian distribution, or finally 3 is sawtooth wave with random frequency. And then in the loop, you repeat, okay, select the frequency, generate the signal. We have discussed all of this so far in the PDF slides. You remove the mean, you normalize to unit variance, you find the delta maximum value, this crest factor, as a ratio of the maximum absolute value to the effective value. And then you run the loop for all the desired entropies. So you select this entropy H from this vector from 1 to 16 if you do the loop, or only for this value 3 if you have this demo equal to 1. Okay, and then what you find this differential entropy for all 3 types of signals. You find this Hx. Then based on differential entropy and chosen entropy of output indices, you select the step size, d. Once you have the step size, you find the expected distortion, simply d squared over 12. And finally, you find the expected SNR ratio as 10 log 10 of signal variance, that is 1, over the distortion, so the expected distortion, ER očekivano. The actual quantization, I divide the signal by the step size, I round it, I get the output index via yi, and I multiply the index by the step size to get the quantized signal, yq. I take the difference of the actual signal and the quantized signal, that is the error, and I find the sample mean of the error, and I find sample mean of the squared signal. So squared error, squared signal, in the ratio they would define SQNR for the empirical, for this realization. So this one realization has some empirical SQNR ratio. And this value should be close to this expected SQNR. So this was this expected SQNR based on the step size and that was derived on the chosen entropy of output indices. And here I would compute the actual PDF for each symbol, as discussed on the slides. And finally, I would find also this expected PDF for each of the symbols, but based on the cumulative density function of the process, not from the empirical, from the realization, but from the process. So I know the CDF of the process, and I can find the probability for each of the quantized values for each of the symbols. And I have this expected PDF for each of the symbols. Now I compute the entropy of the output indices for this case, for this theoretical case, and I find this expected output entropy that is more accurate for high entropy, where the number of samples of the realization is insufficient, but is also true for the case of low output rate. So this theoretically derived probability for each of the class is necessary if you want to compute the PDF for high rate. If you have high rate, then the number of samples that you use to find the probability must be really large to observe all the possible values of the signals that you would like to compute the probability of. So that is the reason why we have to use this theoretically derived probability for each of the symbols. So empirically, but also theoretically derived probability. And finally, it plots the output figures, blah, blah, blah. And now I will run this code. So for this demo mode equal to 1, I run the code. So now it is first sinusoidal signal. It plots 3 different figures. One is this signal and quantized signal. The other plot is a histogram of the quantization error. Okay, and the third plot is no, only 2 figures. So it goes to these examples. Okay, but now I will run this in the loop and compute this. I will compute this for the range of desired entropies. So I simply take this demo to 0, I save it, and it will compute the output quality for this range of desired entropies. Okay, now I run the program. I have to break it. Ctrl-C. Okay, now I run the program again. And it computes this curve. Okay, so it has passed through all of these different values of the desired entropy, and it has found the actual entropy and the actual quality for each of the chosen desired entropies. Okay, that is the plot for the sinusoidal signal. Now, if I change the signal to, for example, it is not sinusoidal, it is sawtooth wave. I simply select here the signal to be signal 3. So that will be uniform distribution. I run the program again. So you saw this image already in the slides. So we have again this deviation for low rate, but for higher rates, this approximation is very close. But the best approximation was for the case of normal distribution. And for this case of, so each time I press enter, it runs a new simulation with another randomly chosen frequency. Okay, so each time I press enter, it will run again, and it will show again the rate distortion curve, but with another example of randomly chosen frequency. But if I terminate the program with Ctrl+C, and finally I select the last example with the sinusoidal, not sinusoidal, with the normally distributed signal, so I will say signal type is 2, and that is noise, uniform, not uniform, Gaussian distributed noise. I run it. Now you see that this deviation is the least possible deviation of all three signals. But also what you can observe that this expected curve is the lowest possible curve, so it has the least offset value, negative offset value of this minus 1.7 dB, because this is the worst case. So the normally distributed signal is the worst case for the quantization, the most complex signal for the quantization, for the given entropy, and for the given signal variance. So more or less this concludes this example, and you will use this code to do the laboratory exercise number 1 on Thursday. But instead of quantizing the signal in time domain, you will do this quantization on each of the coefficients in the transform domain. Okay? And you will find out in these guidelines how should you select the step size for each of the channels. So that is also one question you have to answer. How to select the appropriate step size for the first channel, second channel, blah, blah, blah. And you will see in this discussion in the guidelines that due to this orthonormality of transformation, so this transformation preserves the energy from the time domain to frequency domain, because the transformation is unitary matrix. This matrix is orthonormal matrix. And this transformation preserves the information of energy. So energy is the same in transform domain as in the time domain. And that is the reason that whatever you introduce as a quantization error in transform domain is simply transferred with the same value after reconstruction in time domain. And finally, it turns out, ideally, you should have the same step size in each of the channels. So ideally, the step size for each of the subchannels should be chosen equally. So you have only this step size delta as a parameter. But what is different, you have different entropy codes for each of the channels, because you have different number of symbols in each of the channels. Why? Because the variance is different. So variance of each of the channels is different. First channel has the largest variance, the last channel has the least variance. And for that reason, the information quantity of the first channel is the highest, and it would have the largest number of symbols, and definitely the largest output entropy. Okay? So that is just preparation for the laboratory exercise that you will do on Thursday. Okay, so we have concluded this presentation number 2, and number 3 and 4 we will be doing on not next Monday, because next Monday is Easter Monday. So the week after that, it is April 20th, I think, 20th. This April will be the last lecture I will be giving, and it is also the last lecture prior to midterm exams. So it is the 7th week, and after this 7th week we have this midterm exam. Hopefully it will be held, but also depends on this epidemiological situation. So if it gets really worse, probably the management will say, no, everything is cancelled, go to online teaching, and we will have the final exam as in-person exam, hopefully a few months later when it is better. Nobody knows. So right now it is still on schedule. So in the 8th week or 9th week, I don't know which one, you will have the midterm exam, one of those 2 weeks, 8th or 9th week. But if anything goes wrong with numbers of newly contracted diseases, probably it will be cancelled also, like it was the last year. It was the same situation last year. Also, the numbers were going higher and higher, and management decided that we will go to online only. Regarding the obligations that you have this obligatory preparation for this first laboratory exercise, and it is already uploaded or given in the instructions on the web. So you have here preparation for the first cycle of laboratory exercises. You have to do these tasks, okay? Encode something, encode something. You have to encode your first and last name using Huffman encoder. So compute the statistics of letters in your first name and last name, construct the code, and encode your first and second and last name using Huffman code. And then the same thing with arithmetic code methods, okay? Okay, so this is like a preparation for this laboratory, and then the actual guidelines are those that I have showed you already, okay? You also have some scripts that you will be using, either from this from the second lecture. So from the second lecture, this MT02 MATLAB examples. So examples for the second lecture. So we take this zip file, and in this zip file you will find exactly this MT02 quantization entropy. Okay, the example shown today. And so that will be used as a template, and also you will have the examples for this laboratory regarding the discrete cosine transform, laboratory, first exercise, first cycle, this discrete cosine transform. Okay, so this is one script, very short script. Okay. Okay, move this. I don't know how to move this. Like this. Okay. So it defines this transform matrix depending on the chosen dimension of the transformation. In your case, the dimension would be 8, and this matrix would be 8 times 8. And it is unitary matrix. It means that the inverse matrix is equal to the transpose matrix. So M transpose is equal to M to the minus 1, to the inverse matrix. And this matrix can be then applied to transform the 8-dimensional sequence of equal samples into 8-dimensional vector of spectral coefficients. Okay? Assistant Branimir Dropulic will be guiding you with these laboratory exercises, and it will be done with Teams. So you will connect with Teams on this meeting. You will start the MATLAB on your own computer, and then follow these guidelines and solve the task shown here. So you start with this second task first, so DCT-based answer coding. And the second laboratory exercise will be after the last lecture, so in this April 12th, after this Monday, again I think on Thursday or Wednesday, we will have the second laboratory exercise in the 7th week of the lectures, okay? And also in this 7th week, we'll also have this auditory for recitations. On this recitation, Branimir Dropulic will try to take few examples for the problems you will be solving on midterm exam. So the same type of problems that will be occurring in the midterm exam, he will try to solve several such problems on this recitation. It will be also in this last week. It will be announced, also using Teams. Okay, so more or less it is enough for today. So see you in 2 weeks' time. And also I wish you very best for the Easter holidays. It is not that bright situation as it should be, of course, to go around without any problems, but okay, try to enjoy it as much as you can. Okay, then see you after the holidays. Bye-bye.
Thank you.
Bye-bye, see you.